The work I'm going to present today is a joint work with André Liotier. I'm interested in the following problem. We have a set of points, and those points have been obtained by sampling some shape. And unfortunately, the shape is unknown. We only know it through the point set. And given as input this set of points, we would like to output a mesh that approximates the shape. So this problem has been well studied, in particular when the point set lives in R3. So typically in that case, the shape is the boundary of a physical object, and we are measuring points on this physical object. And given as input those points, we would like to output a surface. So this has application to reverse engineering, but the shape reconstruction problem has also application in machine learning. In that case, the point set typically lives in a very high dimensional space, but the points are assumed to lie to be close to a manifold. So this is the manifold assumption. And for instance, this is illustrated here. For the point set, we have a collection of images. So each image here can be interpreted as a point in a space whose dimension is the number of pixels. And so imagine that, in fact, those images were obtained by taking pictures of a statuette, and the statuette is located on a table that is a round table. And so there is only 1 degree of freedom in the system that you are observing. And so it's typical that the degree of freedom of the phenomenon you're observing is much less than the number of observed variables. And so in that case, you would expect the images, in fact, to lie on a curve, which reflects the fact that there's only 1 degree of freedom in your system, which is the angle of rotation. Okay, so we're going to focus on a particular instance of this shape reconstruction problem, in which the shape we want to reconstruct is a smooth d-dimensional submanifold of some Euclidean space of dimension n. And what we would like to do is output a mesh that would be homomorphic to the shape. That is, we would like to have a bijection that is continuous and whose converse is also continuous. So we would like to recover exactly the topology of the shape. There is something that one can easily obtain. It's a construction that is homotopy equivalent to the shape. There are several possibilities for that. So this means that you would get something that will recover the number of connected components, the number of cycles, and so on. But you are not guaranteed to obtain exactly the dimension of the shape. You may have an approximation that is typically thicker than the shape. And so, starting from this auxiliary construction, you can try to simplify it to obtain something that would be homomorphic. So this gives a list of possible approach. There are direct approaches that have been, so this direct approach has been followed by Jean-Daniel Boissonnat and his co-authors for many years, and they were able to prove that the method that they propose, they developed, is actually is guaranteed, to find some guarantees. there is also, so what we did with André is study a variational approach. And we took inspiration for that from the work that colleagues do in geometry processing, in which they want to optimize meshes by moving vertices with respect to some energy. And there are also another approach, which is that you would construct a rough approximation of your shape and then apply a sequence of simplification like collapses or edge contractions. And in this talk, I will not consider the third approach. Okay, so there are some terms that are useful to shape reconstruction and that I'm going to introduce now. Given a shape A, here, the boundary of this rectangle, which is a curve, the medial axis of a shape is the set of points, M, that have at least two closest points in the shape. So the medial axis of this rectangle is formed of those red curves here. And we consider the projection map on the shape. This projection map is going to be defined everywhere except at the points of the medial axis. And the ridge of the shape is the distance between the shape and its medial axis. So in this particular example, the ridge vanishes here, it's 0. But when you consider a shape that is a smooth manifold, the ridge is positive. For instance, here it would be maybe this quantity. And the ridge has been used to describe the quality of the point set. So, for instance, consider this set of points here and try to reconstruct some curve of some shape from those points. In the middle, it's unclear what we should do. And the reason is because the density of the point set is not high enough compared to the shape that we are trying to reconstruct, compared to the reach of the shape that we are trying to reconstruct. So if we increase the density here, then it seems that things are easier. We will be able to do something. And actually, there is a very nice theorem that was proved by Nyogi, Meyer, and Weinberger, and that has been revisited a number of times, which is the following. It says that if you take the union of the balls of radius alpha centered at the points, that is the alpha offset of the points, then this union of balls, deformation retracts to the shape if the distance, the Hausdorff distance between the shape and the point set is smaller than a constant times the reach of the shape for a well-chosen alpha. So here the problem is that, okay, we have reconstructed, we have output a set, which is a union of balls, but this union of balls is not at all homeomorphic to the shape. And we would like to output what we call a faithful reconstruction. So we define a faithful reconstruction as an abstract simplicial complex, which will be geometrically realized. So this complex is going to be formed of simplices. It will define a domain. And we want also that as we project the domain onto the shape, we get a homeomorphism. So that's what we call a faithful reconstruction. So a simplicial complex K that is geometrically realized, and such that if we consider the restriction of the projection on, to its domain, then as we project the domain onto the shape A, we have a homomorphism. Okay, so I've been told that maybe I should give definitions. So I just recall here that we consider simplices that are abstract. We find it convenient. So an abstract simplex is just a collection, a finite collection, a non-empty finite collection of points. Here, the points will be Rn. We can associate to an abstract simplex a geometric simplex obtained by taking the convex hull of its vertices. And so for us, a simplicial complex will be abstract, meaning that it will be a collection of abstract simplices together with all their faces. Okay, also, the dimension of the abstract simplex is the cardinality of this of the simplex, that is the number of vertices minus 1. And the dimension of the geometric simplex is the dimension of the affine space spanned by the geometric simplex. And when the two dimensions coincide, we say that the simplex is non-degenerate. I also recall that the height of a simplex is the smallest distance of a vertex to the affine space spanned by the other vertices. And so the height vanishes if and only if the simplex sigma is degenerate. And so when I say that I want to consider a simplicial complex that is geometrically realized, I mean that the simplices in my complex are non-degenerate. And also, when I consider geometric simplices associated to the abstract simplices, they have to intersect along a common face, so that the situation in this situation is authorized, but the one on the right is forbidden, because I would have the convex hull of delta and the convex hull of gamma that would overlap, but not intersect along a common face, a common edge. So a very simple example. So suppose I have a shape that is just a quadrangle in the plane with 4 vertices A, X, B, and Y. Then the two triangles, the two simplicial complexes K1 and K2 here are faithful reconstruction. Okay, but the third one, K3, has been obtained by taking the tetrahedron A, X, B, Y on all its faces. And in this case, we don't consider it a faithful reconstruction because the tetrahedron is degenerate first. And even if it was not degenerate by, say, moving the vertices in R3, then the domain would be a tetrahedron, which would not be homomorphic to the shape we want to reconstruct, which is a topological disk. Okay. So we are back to the problem, the reconstruction problem, sorry. We suppose that we have a smooth d-dimensional submanifold, a set of points that sample this manifold, and we would like to construct a faithful reconstruction of that manifold, given as input the point set. So imagine that actually your manifold is flat. There is no curvature. The point sets are, say, in RD. Then we know how to construct a faithful construction of the convex hull of the points. This is easy. We can return the Delaunay complex of the point set. And so I'm going to record that, the definition of a Delaunay complex. So a simplex sigma belongs to the Delaunay complex of the point set P if there exists a sphere circumscribing sigma and that does not enclose any point of P. And it is well known. So for instance, here, my triangle ABC is a Delaunay triangle, and the edge UV is also a Delaunay triangle. And it is known that if the point set is in a generic position, then the complex is indeed a faithful reconstruction of the convex hull. So the point set is in generic position if there exist no d+2 points that lie on a common d-1 sphere. Indeed, for instance, here we have a point set that is not generic. We have 4 points that lie on a common circle. So if we follow the definition of a Delaunay complex, we have that the tetrahedron ABCD belongs to the Delaunay complex together with all its faces, and therefore we don't have a faithful reconstruction of the convex hull. So this Delaunay complex has been well studied. There are softwares like Medial that are available to compute it in small dimensions. So I've brought pictures from the web. The success of the Delaunay complex is due to its many properties. On one hand, we have a very neat characterization of its elements. And on the other hand, the Delaunay complex is known to optimize many functionals. And in particular, it minimizes the Delaunay energy. And I will go back to this after in the talk. So what we would like to do is to generalize this construction when the point set sample a manifold. And I would like so to define a simplicial complex with vertices P that will enjoy those two properties. First, a geometric characterization of its elements, and second, we would also like this generalization to minimize the Delaunay energy under some conditions. So this gives us the roadmap for this talk. So first, we're going to define this Delaunay complex generalization for points on the manifold. Then we're going to state conditions under which we indeed have a faithful reconstruction. Third, we're going to define a minimization, the minimization problem. And finally, state conditions under which the solution of this minimization problem will be our Delaunay complex generalization. So when we started the work, we were having a clear idea of what would be the minimization problem, what we wanted to minimize. And then we saw that there was a property that was key. And the solution, we called the solution that we were having the log complex. And then to prove that this log complex was indeed a faithful reconstruction, we decided to study instead the flat Delaunay complex. And it turns out that this flat Delaunay complex is not very, it's just a small variant of the tangential Delaunay complex that has been studied by Boissonnat, Gauche, Dyer, and the co-authors. So in this presentation, I will speak about the flat Delaunay complex because we believe it's, I think it's a good compromise. So again, we have this manifold M, a point set P, and we're going to define the flat Delaunay complex. So consider a point V in your point set. The point set is not necessarily on the manifold. It can be slightly noisy. So project the point set, the point V onto the manifold, you get V prime. Consider the tangent space passing through V prime. The construction depends upon a scale parameter that we are calling ρ. So we are going to restrict the point set to the ball centered at V prime with radius ρ prime, ρ. So this is, we select a subset of the points. We project them onto the tangent plane, onto the tangent space. We compute the Delaunay complex of the projected points. We collect only the simplices in this Delaunay complex that pass through the vertex V prime. So for clarity, I've translated the tangent space so that we can see something. And then we are going to lift up those stars, the simplices in the star. That is, we're going to define the pre-star. So the pre-star, a simplex belongs to the pre-star if it's in this ball of reduced row here, and if this simplex, the projection of the simplex onto the tangent plane belongs to the star. Okay, so as you project simplices in the pre-star, you obtain your star. So that's why we call it the pre-image. Okay, so we have this construction for each point V in our point set. The flat Delaunay complex is just the union of all those pre-stars. So by construction, the simplices in our flat Delaunay complex are rho small because they are contained in a ball of reduced row. Yeah, I'm going to say that a simplex is rho small if it can be contained in a ball of reduced row. And also, this flat Delaunay complex can be constructed by computing one Delaunay complex per point of dimension d. Okay. So now the question is, okay, we have those pre-stars, one for each point V. And it does not seem too complicated to, it seems reasonable to assume that we will get locally some faithful reconstruction. But as we take the union of all those pre-stars, do we get globally a faithful reconstruction? So here is an explanation of why things can go wrong. Imagine that you have your manifold, that would be here a surface, say, on 4 points A, B, C, D on your surface that are almost co-circular. So you want to compute the pre-star of A. You project your 4 points on the tangent plane passing through A. And you want also to compute the pre-star of B. And you do the same thing on the tangent plane passing through B. But because the 4 points are almost co-circular, the Delaunay triangulation that you get in the two tangent planes are different. The diagonal that you're going to choose in both cases is different. So that in the pre-star of A, you will get two of the triangles of the tetrahedron ABCD, and the pre-star of B will get the two other faces of that tetrahedron. So that in the flat Delaunay complex, you will get the 4 faces of the tetrahedron. So if in addition you have all the points elsewhere, you would get this small cavity in your reconstruction, and you don't have homomorphism. So you don't have a faithful reconstruction. Okay, so how to avoid this? We need to stay away from those situations, actually. So we introduce a quantity that we call the protection of the point set as scale rho, on which measure how far we are from the previous situation I've just described. So you take a simplex, a d-dimensional simplex sigma. You take a point Q in the ball centered at sigma with radius rho, and project the point Q on the affine space spanned by sigma. Consider also the circumsphere passing through sigma, and the distance from the projection of Q this circumsphere. This will give you a distance, and if you do this for all points, for all d simplices sigma on all points q close to sigma, you take the minimum of all those distances. This gives you the protection of the point set at scale rho. Okay, so I'm going to state our first result. So it looks like this, and it states conditions under which we have what we want, that the flat Delaunay complex is a faithful reconstruction. And among the conditions, we have safety conditions on sampling conditions and safety conditions. So the conditions can be classified in two types. Okay, sorry. So for the sampling condition, it's something realistic and usual. We will assume the point set to be delta accurate, meaning that the points are at distance at most delta from epsilon, from the manifold. We also assume that the sample, the point set is epsilon dense, meaning that any point on the manifold is at distance at most epsilon from a point set, from a point of the point set. Okay. We have then those safety conditions. So I'm not going to detail this, but it gives a upper bound or lower bound of some quantities that describe the quality of the point set. So for instance, you will have the first condition that tells you that the point set must be well separated, must be separated in the distance, the smallest distance between two data points must be larger than some quantity, and so on. So you have also to control the angle that make d simplices with the manifold, the height of the d-dimensional simplices, and also you have to lower bound the protection that I've just introduced before. Okay. So in a nutshell, what the theorem says is that we have sampling conditions and we have safety conditions at scale rho, and then we get a faithful construction. So what we did is to establish this result is that we first show that starting from the sampling conditions and the safety conditions, we could establish some structural properties, and from those structural properties, deduce that we have a faithful construction. And we were kind of happy with the second proof here because it was kind of short, but I'm going to skip this. And so I would like to talk about the variational approach. So the first step is done. We have defined the flat Delaunay complex, and we have a geometric characterization of its elements. And now we would like to prove that this flat Delaunay complex, in some sense, minimizes the Delaunay energy. So for this, I have to define what is the Delaunay energy. So we are back to the Euclidean case. We consider a point set P in Rd, and let T be a triangulation of this point set P. So there is a famous construction that consists in lifting the points in Rd plus 1 that on a paraboloid. So consider the paraboloid whose graph is the norm squared, okay? And the paraboloid is in Rd plus 1, and you project vertically the points in your point set onto this paraboloid. So as you do this, you can also lift each triangle, so it's each simplex in your triangulation up, and you will get a triangulation, a surface that is piecewise linear and that is above your paraboloid. And the Delaunay energy is the volume that is between your paraboloid and your lifted triangulation. So it has been represented here in d equal 2 and here for d equal 1. So the Delaunay energy will correspond to the yellow zone here, the yellow region. And it turns out that if you compute the Delaunay energy for all possible triangulations, the one that minimizes the Delaunay energy is the Delaunay triangulation. So the Delaunay triangulation is the triangulation of the convex hull of the points with the smallest Delaunay energy. And it turns out that this Delaunay energy has a very nice expression. So to compute this volume, you can start by considering 1D simplex, the lift of this 1D simplex, and compute the volume between the lifted simplex and the paraboloid. And you sum up over all these simplices in your triangulation. And the volume here that you have associated to, that is between your lifted D simplex sigma and the paraboloid, is what is called the Delaunay weight of sigma. And it has a beautiful intrinsic expression that depends upon the volume of sigma and the length of its edges. And so it means that I've explained everything, assuming here that my point set P is in some d-dimensional Euclidean space, but actually I can take this formula and apply it to any soup of these simplices that lie in some higher dimensional space, Rn. And this is intriguing. So it means that you can take a point set P, you can take a set of triangles there, compute the Delaunay energy, and try to minimize this over all possible triangulations, all simplicial complexes that triangulate your manifold, and see what happens. Okay, so here there is a problem in this formulation. It's that the constraint here is clearly not linear. And we would like to transform this problem into a convex problem so that we could solve it efficiently. So in order to introduce the idea, I'm going to consider a simpler problem that is the following, a one-dimensional problem. Imagine that you have a graph G, and each edge in your graph has a weight, W of E, the weight of E. You take two vertices in your graph, A and B, and you ask for the shortest path connecting A to B. And I would like to play a bit with this problem so that it justifies the formulation that I'm going to present after. Okay. So if first I'm going to play with the weights that we can take. If I take for each edge the length of the edge for the weight, and if in the I have the edge connecting A to B, then the shortest path is clearly the edge connecting A to B. Okay, but now I'm going to consider I'm going to give to the edges a weight that is the length of the edge square. And here, if I try to compute the shortest path connecting A to B. Then imagine that you have 3 points, A, B, and C. And C is outside the disk with diameter AB. Then it's shorter to take the segment AB. But as C is entering the disk, it becomes, because of the Pythagorean theorem, it becomes more interesting to pass through the point C. It will provide you a shorter path. Okay. So now take the length for the weight of the edges, the length of the edges cubed. And actually, this coincides with the Delaunay weight that we have introduced earlier. And so the consequence of that is that your shortest path is going to go through the denser parts of the point cloud. Okay, so to compute this shortest path, we know that we can apply the Dijkstra algorithm and that it will solve this efficiently. But the problem is that we have in mind the fact that we want to extend this to d-dimensional manifold, and this approach does not extend well. So there is a trick here that we can use, which is to enlarge the search space. That is, we are going to replace the set of paths by a vector space, which consists of the one chains with coefficient in R. So we give each edge in the graph an arbitrary orientation, and the one chain is just a vector, a vector written in a basis formed by those oriented edges. So it's a formal sum written like this. Okay, so this is a vector, and it will have a collection of coordinates, one for each edge. We can associate to a chain gamma the boundary of that chain, which is a linear operator. So since it's a linear operator, we can define it on the elements of the basis as follows. So the boundary of the HE will be the vertices at the end of the edge minus the vertex at the start of that edge. Okay. And here is a small example of one chain. So now you have to affect to give a coefficient, a coordinate to each edge. So an edge now carries first the weight of that edge and then a coordinate. Okay. And here is a small example of one chain gamma that is expressed like this. Okay, and whose boundary is precisely B minus A. Okay. So now we have transformed our problem into finding a one chain that minimizes the Delaunay energy. So we are considering a weighted ℓ2 norm here first, that is expressed by this. Under the constraint, the boundary of this one chain is B minus A. And if we take the ℓ2 norm, then in fact, we are computing an harmonic form, and it is known that the solution will spread everywhere. So on every edges, you will have a small part of the one chain that will pass through there with a small coordinate. And so to compute the path, that's not a good idea because you don't have a path, actually, it goes everywhere. And there is an analogy, a physical analogy of this phenomenon, in which you imagine that the graph G is an electrical circuit, and the coordinate of the one chain gamma of the harmonic, the one that minimizes this, that is the solution of this problem, provides you the current that passes through the edge. Okay, so how to avoid this? We change the norm. We take the ℓ1 norm instead, associated to the one chain. And we know that the solution in that case is expected to be sparse. Okay, so generalizing all this to higher dimension, we are back to the formulation of this variational problem. So we have our point set P. Suppose that we are going to build a simplicial complex with vertices the points of P. And this simplicial complex is going to provide a rough approximation. It's going to play the role of the graph. Okay. And what we want to do, is to find the D chain gamma that minimize the Delaunay energy computed with an ℓ1 norm, okay, subject to the constraint that this D chain gamma is a cycle and also satisfies some normalization constraint. So the normalization constraint, you take a point M0 on the manifold, you look at all the D simplicities that projects onto the manifold, and you keep those that cover M0, and you sum up the coordinates of those simplices. And this is what we call the load of gamma above M0. Okay, so now the constraints are linear. The norm is L1, and so we get a convex optimization problem that can be solved using slack variables by linear programming. So we are happy with the formulation. And what we were able to prove is that under some sampling conditions and safety conditions, the solution of this problem is unique and encodes the flat Delaunay complex. So if you look at the safety conditions, they are slightly more complicated, say, but that was what we were able to do. In a nutshell, we take a point set P that samples sufficiently nicely M, and that is sufficiently safe at scale ρ. And the problem, this minimization problem, has a unique solution which encodes the flat Delaunay complex. So somehow it's not astonishing, because the flat Delaunay complex has been defined locally as small pieces of Delaunay triangulations. And the Delaunay triangulation is known to minimize the Delaunay energy. So locally, we are minimizing this energy. But what was not at all clear and not at all easy to do is prove that we have actually a global minimizer of the Delaunay energy. Yeah, I'm going to skip details of why this was complicated, but here are the results of some experiments. So we started with point sets. We computed the Rips complex. So the Rips complex is obtained by connecting points, the Rips complex at scale, say ρ. You connect points that are at distance less than ρ, okay? And then you add a triangle if the three edges are there, and you add all the clique of this graph. So you get the Rips complex. Then we computed in the second column the harmonic form. On the coordinate on each triangle, the value of this coordinate is given by the color. So if it's white, it's a small value. If it's blue, like this means that the coordinate on this triangle is close to 1. And so you can see that as we compute the harmonic form, the solution spreads everywhere. But as we minimize with the ℓ1 norm, then we get the reconstruction. We get the surface. So at least in the two first experiments, in the last one, so we have this two chain, and here where the surface has a high curvature, the chain splits up, and we did not recover a surface, so we are not under the conditions of the theorem anyway. So in conclusion, we have two research reports that are available for more details, and also we will present the variational approach to sausage. In the future, we would like to focus more on the algorithmic aspects of this problem, and also play a bit with the energy. So see if, for instance, we could consider anisotropic energy. So thank you for your attention.